Hey everybody. So we've now got this tool called the limit in hand, and we're going to use it and return back to the problem that we were investigating in the beginning, the slope of the tangent line. So let's just remember what the problem is exactly. We have a function, call it f. So just drawing a little piece of my function f. And let's say this function is defined around a point A. So here's the point A, f of A. And we want to find the slope of what we call the tangent line, right? So we actually haven't defined it specifically. That's what we're going to be able to do now, but we've used some intuition around it. And the way we've intuited what this tangent line is we imagine that we move a little bit away from A. So H is just some little number. And here I've drawn it so that H is on the positive side. It doesn't have to be. H can be negative, so we'd be below A, but I'm just going to draw it here. And so H, remember, is small, and we know that our function is defined near A, so some interval around A. So eventually H can be small enough, however small we need it to be, so it's in this place where F is defined. This will be the point A plus H, F of A plus H, right? And so we can imagine drawing the secant line through these 2 points, okay? So we want the tangent line at the point A, and this secant line that I've drawn here is a decent approximation. And the slope of the secant line well, we just take the difference in the y coordinates, the output values, and the difference in the input coordinates. All right, so in the denominator, I can cancel, and we'll get, maybe I'll write the secant line here. This is f of A plus H minus f of A all over H, because that A and the negative A in the denominator cancel, right? So this gives us a formula we call the difference quotient sometimes for the slope of the secant line, right? And so what we imagined doing and what we did numerically, we would plug in values for this where we let H be smaller and smaller and smaller, right? And we saw that often when we did this, excuse me, the numbers that would come out seem to be getting closer and closer to something, right? So that's where we, how we were doing this when we began. And so we took a turn to say, let's figure out how to deal with this getting closer thing. And we came up with limits. And so here's what we can do now to finish this problem. We imagine making H small. And so in this picture, you imagine those 2 points, the point at A staying constant, not moving, H getting smaller, so the other point's getting closer and closer and closer. And we're consistently taking the slope of that line, and we see what the limit is as H gets closer and closer to 0. And so we get the slope of the tangent line is exactly the same formula, except instead of being an approximation, we take the limit as H goes to 0 of f of A plus H minus f of A over H. And I should say, let's add a line in here. The slope of the tangent line at x equals A is this configuration. So all we've done now is, in the beginning, we were imagining and numerically plugging in numbers that were smaller and smaller and smaller. We now have the limit to deal with this to make sense of this without having to make guesses. Okay, now of course, well, maybe not of course, let's add one more thing here, provided this limit exists. Oops. Right, and it might not be obvious, but, and we'll deal with this in a later video, it doesn't have to exist. There's no guarantee that this is even possible. We want it to be. We want to be able to do this. And in most of what we look at, and in most of what people care about, this is possible. This limit does exist, but there will be instances where we can't do this. So let's do an example with this. Let's grab this little piece. And do an example. So just going to leave this over here for us to refer to. Okay, so let's use this and find the tangent line to f of x equals 1 over x at x equals 1. Okay, so all we need to do is apply this formula, the slope. So let's, before we say that, to find a tangent line, so to find the equation of the line, we need a slope and a point. Right? Well, the point we have is easy. We know that f of 1 is equal to 1. So this curve goes through the point 1, 1. Okay. The slope, we now have the ability to get, or we hope we do, if this limit exists. So let's try taking this limit. So we want the limit, so our slope will be equal to the limit as h goes to 0. And right now I'm just copying it, right? So we're finding the tangent line at x equals a. In this case, it's at x equals 1. So we'll have 1 plus h minus f of 1 over h. Now let's put in the expression for this function. So this is going to be 1 over 1 plus h minus 1 over 1. All of this over h. This is an ugly little expression. Let's do a little scratch work off to the side. So putting aside the limit for a minute, I want to do some algebra. So remember, one of the last things we learned with limits was when we have something like this, we have a problem here. This is essentially a rational function. It's a little bit ugly. We'd have to mess with it, but 0 is not in its domain. So we can't just plug 0 in. You can try plugging 0 in. We get 0 over 0, which is not defined. So what we're going to try to do is find a function equivalent to this one everywhere except at 0, and hope that this exists, and then we can take its limit, right? And it's something we'll know how to take the limit of. So what we're going to do algebraically is play with this thing, right? We're going to let our instincts, which really means the pattern recognition we've picked up through practice, guide us here. And looking at this thing, one of the things I hate the most is the double fractions. And so I'm going to try to get rid of some of those double fractions. So let's look at the numerator first of this thing, just doing some scratch work over here. 1 over 1 plus h minus 1 over 1 is equal to 1 over 1 plus h minus 1 plus h over 1 plus h, right? I'm just writing the number 1 or 1 over 1 a little differently. These are both, this and this are both equal to 1. So I've changed nothing by just writing it in a different format. But now I have a common denominator. So I have 1 minus 1 plus h over 1 plus h. I'll have 1, well, let's just write it out. 1 minus h over 1 plus h. The 1 minus 1 is a 0, and I've got negative h over 1 plus h. Okay, so we now have negative h over 1 plus h, that's our numerator, divided by h, which is equivalent to multiplying by 1 over h, the h's cancel, and we're left with negative 1 over 1 plus h. Okay, so this expression is equivalent to our original expression, right? 1 over 1 plus h minus 1 over 1 all over h. Those are equivalent except at one place, when h is not equal to 0, because of this move right here. When we cancel these h's, right, this is a perfectly reasonable thing to do for any number, for any real number, except for the number 0, right? When there's a 0 over 0, we can't cancel this way. And so we have to say, well, this is true as long as we outlaw the point 0. Luckily for us, limits don't care about 0. And so the limit as we go to 0 doesn't care about that point. And so we now have this function that is the same function, the same expression, except at 0. And so these two things, right, this line here and this line here, have the same limit. This limit is now easy to take because this is a rational function and 0 is in its domain. So we simply evaluate it. We get negative 1 over 1 plus 0, which is, of course, negative 1. So the slope of the tangent line is negative 1. Okay. Our goal was to find the equation of the tangent line. And so now we have a point and we have the slope. So I can write the equation. So the equation of the tangent line, we'll use the point slope form. So I'll have y minus 1 equals negative 1, x minus 1. And there it is. This is the equation of the tangent line to the point. This is the equation of the tangent line to the function 1 over x at x equals 1. We can clean it up if we want. So maybe I'll rewrite this. I'll add 1 to the other side, distribute this negative 1. I get negative x plus 1. Adding that other 1, I get this. So we're looking at negative x plus 2. Right? Notice this point, this line goes through the point 1, 1. If you plug in 1, 1 comes out, right? That's always going to be true of your tangent line. Knowing whether we got the right slope is a little harder to understand. Let's jump over and look at a graph of this to see what this looks like. So here's our function. I'm zoomed in pretty close to the point. Whoops. That's the point 1, 1. I don't know why it won't let me select that point. But that is the point. Oh, I can just have it label it. There we go. There's the point 1, 1. Right? This blue dot represents 1 plus the point at x equals 1 plus h. So in this case, I have h being negative. So you can see that h must be negative 1/2 because the x coordinate is 1/2. 1 plus negative 1/2 gives me positive 1/2, and the output value is 2. If I can change h, making it closer and closer to 0. We zoom in on that point, or I can also go from the other side. Right here, it's equal to 1/2, and I can make it closer and closer to that. We imagine the secant lines through these 2 points. Right? These are our approximating lines that we talked about a minute ago. Notice they're getting closer and closer to what we imagine being the tangent line. But then, of course, when h equals 0, you can see this equation I have for those secant lines has a 0 in the denominator. Right? And so it doesn't, the computer doesn't know what to do with that, right? But we just discovered this tangent line. So here's the equation we came up with a minute ago. And you can see that solid blue line, the thing we call the tangent line, goes through the point 1, 1, and it looks just like what we imagine happening right when this dotted blue line disappears. Right? That's right when that happens. It comes back on the other side. Okay. Let's do one other thing. Let's zoom in here. The tangent line goes through this point, but it also looks incredibly similar to the graph of the equation, right? So if I take that blue line off, you can see it's barely different at this point. We're zoomed in very close, and they're barely different, right? This is not the only line that goes to that point. For instance, the line y equals x, let's make it a different color, also goes through that point. Orange, right? But it doesn't look at all like the function, right? The function, that red line and that orange line are crossing very much at odds with each other. But this tangent line looks nearly identical. And the closer we get, the more they are the same. When we zoom out, sorry, let me adjust this. All right. There we see the red line, the function, and the blue line, the tangent line, don't look so similar anymore, right? But they both go through that point, and you know, when we zoom in, you can even see here, near that point, they're doing the same thing, right? That's what this tangent line is doing for us. What's our function acting like at that point? At that point, our function acts like this line. As soon as we move from that point, it starts acting a little differently, right? We can see that it's for instance, as we move to the right, it's getting less steep. It's becoming more flat, a more horizontal function. If we found the tangent line at a different point, we'd have a much different slope, okay? So there's our tangent line there that we got with this formula. And because this is such a big problem, meaning it's something we're very interested in doing, we give the slope of this tangent line a special name. So this slope of the tangent line is what we call the derivative. Let's capitalize it. It's pretty special. In particular, we're talking now about the derivative at a point. We'll do something a little different in the not too distant future, but for now, we're talking about the derivative at a point. So let's give ourselves a clear definition. Let's let f of x be a function defined on an open interval that contains a. The derivative of f of x at a is denoted f, so we put a little apostrophe, we say f prime of a, or the derivative of f at a, right? These are different ways we refer to it, and is defined as f prime of a is equal to the limit as h goes to 0 of f of a plus h minus f of a all over h, provided the limit exists. Okay, so this is the derivative. Okay, notice this is just the slope of the tangent line. So we give the slope of the tangent line this special name, the derivative, but the right side of this equation is just what we did up above for the slope of the tangent line, and that's what we're going to call the derivative. Okay, so let's make that connection clear. The derivative at a point is the slope of the tangent line, which we also can think of as the instantaneous rate of change. Let's say more specifically of f of x with respect to x, okay? We'll talk more about that in another video. We've seen this a bit already, the idea of the instantaneous rate of change, but the derivative at a point, the slope of the tangent line, and the instantaneous rate of change of f of x with respect to x, meaning how does f change as x changes? That's what a slope tells us. These are the same thing. They're different ways to refer to the same thing, okay? And so we always need this connection in our heads, right? When we start computing lots and lots of derivatives, it's easy to kind of put the reasons for it and what it represents behind us and forget, but this is always what it is getting at for the slope of the tangent line and the instantaneous rate of change. Okay, one last thing I will do right now. I just want to present an alternative notation. It's only slightly different, but it is out there, and so I just want you to see that it's equivalent. So I'm just going to do exactly what we did before. To begin this video, we have a function, f of x. We're interested in the derivative of this function, or the slope of the tangent line of this function at the point a, f of a. So we move a little bit away, right? And before we called this a plus h, right? So we had this distance in here was just h, so we're a plus h. Remember, I'm again drawing it on the positive side. H could be negative. Alternatively, we could just call this point x. It's just a different point than a. And so this would become x. We can still draw our secant line. We can still write an equation for the slope of the secant line like this. And if we want to then shrink the difference between them, remember with this first definition, h represented the difference between them. So to shrink the difference between a and a plus h, we just let h go to 0. Instead, we're just going to let x go to a. And this is just an alternative notation for the derivative, okay? It means exactly the same thing because as x goes to a, and again, I drew x on the positive side, but there's nothing that says it has to be. I could have drawn x down here. X is just like h is something that's changing, x is something that's changing, and we're seeing what happens as it gets closer and closer to a, or in the case of h, goes to 0 because then the difference between a plus h and a goes to nothing, right? So another way you can look at it, they're equivalent. I tend to like the one with h, but there's nothing wrong with using the other one. Sometimes computations can become slightly easier in one form or the other. I just stick with one, and I find the one with h, this one that I presented first, to be typically the easier one to use anyhow. And it's rare that I decide to go the other direction, but it's easy enough to. It's the same picture, right? It's just representing things slightly differently. Okay, that's going to be it for this one. We'll do some more examples of finding the derivative at a point, or the slope of the tangent line, or the instantaneous rate of change. And we'll talk more about that connection in the next couple of videos. Okay, thanks everybody.